Now, we've finished walking through the mechanics, so to speak, of simplifying these radicals, but what I haven't mentioned to you yet, and I need to because it's very important, is this idea known as the principal root. There are some rules involved when we are taking or simplifying radicals, especially when those radicals have an even index, and that is we always want the positive root. So we're going to have to go back and fix some of our answers to make sure that we did that. So how do we fix answers? Well, we use absolute value symbols. So what I'm going to talk to you about right now is when to use those absolute value symbols. Now, the first thing I want to say about that, so put a little star in here. This is only when working with variables. We don't need to worry about using absolute value when we're working with numbers. We can just take the positive root. We just take the positive version of our number answer, no big deal. It's only when we're working with variables that we would actually need absolute value symbols to ensure that we're taking the positive root. Also, it only is required when we have a situation that we call even, odd. This is if you have an even index on your radical, an even power inside your radical, and an odd power as a result after it's been brought outside the radical. This is the trifecta, even, odd. So it looks something like this. We'd have an even index, so it'd be an even number right here that's outside of our radical sign. We'd have a variable, because it only matters when we're dealing with variables, right? If it's a number, we can just take the positive. And that variable would be raised to an even power. So this is even index right here. This is an even power inside the radical, so that's right here. And then when you reduce, when you divide power by index, these two even numbers would divide to be odd. For example, it could maybe be 6 divided by 2, and then I get 3. Or 2 divided by 2, and then I get 1. So it's when you get a situation like this, so my result after simplifying is odd, the exponent's odd, this is when I would need to introduce or insert some absolute value symbols around my final answer. So I just want to talk to you a little bit about why that is the case. Why is it when it's even, odd, I need to insert these absolute value symbols? It has to do with this fact that multiplying an even number of negatives results in a positive. This one fact is what creates this main issue. And let me kind of walk through how it becomes an issue. Well, first of all, we can see that when you multiply an even number of negatives, 2 or 4 negatives, like -3, the negatives cancel each other out and give you a positive result. So we see it here with 2, and then when you have an even number that's larger than 2, if it's even, it can be broken into pairs of 2. And every time you have a pair of 2, those negatives will cancel, giving you a positive. And this will break into pairs, and then those positive results multiply together to give you one final positive result. See, multiplying an odd number of negatives doesn't have that problem. It just results in a negative. So, for example, let's say I had 3 factors of -3. You do -3 times -3 times -3. Yeah, the first 2 will cancel and become +9, but then you'll have like 1 left over. With an odd number, you'd always have 1 left over after all of your pairs are done. So you'd have a +9 times a -3, and then that results ultimately in a -27. So this has an effect on both what you're allowed to plug in and what can come out of an even root, and only an even root. It doesn't affect odd roots, just the even roots. Let's see why. Because let's say you want to take an odd root of -27. That's no problem, right? We just saw a second ago that if I had 3 identical negatives, and in this case -3, and I multiply them together, that gives me a negative. So I can easily find groups of 3, right? Because when you're doing a cube root, you're looking for groups of 3. I can easily find groups of 3 negatives that result in a negative, right? So it's totally possible and not hard at all to take an odd root of a negative. You just get a negative answer. But what about when you're trying to take even roots of negatives, like a square root of -9 or a fourth root of -81? You might think, well, I know the square root of 9 is 3, so then maybe square root of -9 is -3. But then we just saw earlier, well, no, because I'm looking for groups of 2, right? To have a square root, it would have to be a perfect group of 2. So I'd have to multiply the same number to itself. But when I multiply a negative to a negative, it turns positive. So there is no real number that I could multiply to itself that would equal a negative, right? This is going to end up being an imaginary number. And similar with the fourth root of -81. We might think, well, I know that 3 times 3 times 3 times 3 is 81. So I know the fourth root of 81 is 3, so maybe this is -3. But we saw earlier up here, actually no, when I took 4 -3s and multiplied them together, I also got positive 81, not -81. So that's posing a problem right here, because multiplying an even number of negatives results in a positive. So again, this is an imaginary number. This is not a real number. So when we're working with these things as functions or as expressions, we want to work with values that are only going to result in real numbers. We do not want to work with values that result in imaginary numbers that have the number I. So as a result of that, the domains or the inputs of these even roots must be positive. They have to be restricted to be positive. So we basically avoid taking the square root of -9, and we avoid taking the fourth root of -81. We just don't do it when we're working with real numbers. So when you have functions or equations that look like this, the square root of x or maybe the fourth root of x, or actually anything of this form, right, an even root of x or x to an odd power, something like this, we automatically sort of restrict the domain so that the variable x would be positive. That's sort of automatically in place in this scenario. And we do this so that all of our outputs will be real numbers. So this is the first effect that this has on even roots, is that the insides need to be positive. Now the other effect is on the output of an even root, the range of an even root, because since multiplying an even number of negatives results in a positive, then when you go backwards to take an even root, there's two possible outputs. There's two possible answers to that, a positive and negative root. So when you get to something like this, right, square root of 9 or fourth root of 81, the question is, which one do I choose, right? The square root of 9, it could be 3 or -3, because we know 3 times 3 is 9, and we also know right here, -3 times -3 is also 9. And same here, fourth root of 81, I don't know, is that 3 or is that -3? I'm not sure, big fat question mark, because I know that 3 times 3 times 3 times 3 equals 81, and so does -3 times -3 times -3 times -3. So even roots have this dilemma, like which one do I choose? But odd roots don't. The cube root of 27 is just 3. Because if I were to take -3 times -3 times -3, I'd get -27, not positive 27. So there's no question. This is like easy. And also, I can take an odd root of a negative for the same reason, and I just say, oh, it's -3, right? -3 times -3 times -3 is -27. So I know it's either one or the other when I'm working with odd roots. It's either going to have a positive root or a negative root. It's when we're working with even roots that we have this situation of, well, I don't know which one it is. Which one do I choose, positive or negative? So the choice has been decided by this thing called the principal root. The principal root is what we are defining this symbol to be. When you see these radical symbols that are even roots, we understand that those are referring to the principal root, which is the positive root. We are being told to restrict the outcome to be only positive. So what this does is it makes it a little bit easier for us to evaluate these. We know exactly which answer to choose. And it'll become helpful later when we're working with what are called inverse functions. We haven't gotten to that yet, but we will. And in those situations, we want to work with functions that have only one output for each input. We don't want to work with ones that have multiple outputs for each input. So we have restricted also the range of these even roots to be only positive. So now, take for example something like this. I've got my even root and I'm plugging in a negative, and you might be like, wait, we're restricting the domain to be only positive. but I'm raising it to an even power. So look at this. We square first, right? Order of operations says square first. And so that square, that power of 2, basically turns this into a positive, making it okay for me to have this negative inside the radical, because the square is turning it positive, and then I can easily take the square root of 9 and just say 3. And I know I'm supposed to take only the positive root, so I just take the 3. But what if I didn't know that this was negative 3? And you might be like, how do you not know? It like literally says it right there. Well, what if it was disguised as x? Okay, so I've got a square root of x squared, which doesn't look that menacing, right? It looks fine to me. But what if that x was negative? Well, see, normally when we're taking an even root, we restrict the domain, right? We restrict the domain to make sure it's only positive. But when you put an even power on the x, it's kind of removing that automatic domain restriction. And actually in this scenario, x can be negative now, because this even power right here will turn it positive. We just kind of saw that. But see, I don't know it's negative 3, so I can't just say, oh, negative 3 squared is 9. I can't do that when I don't know what it is. So instead, I simplify it using that property we saw earlier where you take the power and you divide by the index, right? This is an index of 2. So I did take the power of 2 right here, divide it by the index of 2, and I end up with 1. So supposing I did that with my negative 3 to the power of 2 over 2, I'd get negative 3 to the first power. But that's a negative. See, when we're working with numbers, we just know we're supposed to take the positive square root of 9. Oh, that's 3. But when we're working with variables and we don't know exactly what they are, and it could possibly be some kind of negative, like negative 3, for example, we basically put an absolute value around it to make it the positive. So this is the setup that we have to be careful about. It's when you have an even power under an even root. And even more so, if you had an even power under an even root, like we had here, 2 under 2. But then when you divided them, this even power divided by this even root equaled an odd power, right? 2 over 2 is 1. That is when you need your absolute value. Okay, so we know that this is the setup that poses a threat, right? Even index, even power on the inside. So now let's look at this example, because this also poses a threat initially, right? An index of 2, because that's what a square root is, so it's even. I've got my even power, right? So I've got negative 3 to the 4th. X is allowed to be negative here because I raise it to the 4th power first. And that gives me a positive inside the square root, making it okay for x to be negative here. And then we just square root 81 equals 9. No big deal when we're working with numbers, right? But what if we don't know what this number is? And again, you're like, Ms. Lasner, it's negative 3. It's like right in front of your face. But what if it was called x? I didn't know what it was, but maybe x is negative 3 and I just don't know. It's like a negative in disguise. And since I don't know what it is, I can't just raise it to the 4th power and make it 81. I have to instead simplify it this way. I have to take the power of 4, divide it by the index of 2, right? 4 over 2, which is x squared. But look here, if x was really negative 3, right, and I had negative 3 to the power of 4 divided by 2, which is 2, negative 3 squared would automatically end up being positive. Look, I didn't have to do anything different in this method than I did here. It automatically ended as a positive root or as the principal root. So I don't need absolute value in this scenario if I end with an even power, because that even power, even if my x was negative, like negative 3 for example, the even power would turn it into some kind of positive number. So I don't need absolute value in the case where it ends with an even power. So again, it's only when the resulting power is odd, right? Because we're supposed to have only a positive answer, but this x might be allowed to be negative now because it's being raised to an even power. But if it comes out as x to an odd, that's when you need the absolute value. You don't need to worry about it if the resulting power is even. So let's recap here. Only even roots pose the problem because only multiplying a negative number an even amount of times results in a positive. So it's even roots that have to have a restricted domain, right? Only the inputs can be positive, as well as a restricted range. Only the outputs can be positive. Odd roots don't have that issue. They're exempt from needing absolute value, so we don't worry about it if the root is odd or if the index is odd. Also, we only worry about it if we're working with variables, right? If we know what the number is, we just square it, make it positive, and take the positive root. We don't worry about absolute value when working with numbers, only when working with unknowns, variables. If the variable under the radical is raised to an even power, that is when the domain suddenly opens up to include negatives. That's when we might have a potential output being negative. So we have to watch for the outputs, but only in that case, right? When you have an even power under an even radical. We watch for the output. If the output's raised to an odd power, it could be negative. So that's when we put absolute value around it. That was this example right here. So only when that resulting power is odd do we need to worry. If the output ends up being raised to an even power, we don't have to worry because the even power will turn our output positive already. The example we did earlier when I had negative 3 to the 4th power underneath that square root. When I simplified it, I ended up with negative 3 squared, which already was positive, and that would look something like this. So I would not need to put absolute value around my even power. So only the trifecta, only even radical with an even power underneath resulting in an odd power requires the absolute value. So lastly, what we need to do now is go back through our examples and find the ones that need absolute value. So we're looking for even indexes, even powers under the radical, and then odd resulting powers. So the only ones that even had variables, it doesn't even start till number 9. And number 9 is okay because it had a plus or minus sign in front. So that means I'm allowed to have positive or negative, so it doesn't really apply here. It only applies when we're looking for the principal roots. So number 10 is a possibility because I have an even index and an even power, but it ends even. So it's fine the way it is. It doesn't need absolute value. 11 is an odd index, so I don't worry about it at all. That one's fine as is. It's only if you have an even index. 12 is an even index, so that answer was fine as is. It doesn't need to be changed. But 13, I want you to highlight this one. We're going to have to add absolute value to our answer. This has the trifecta. I've got my even index. I've got my even power inside the index, and it ends odd, right? It looks like this. Even index, x is to an even power, but then on the outside, x is to an odd power. So I need to put that an absolute value. So we're going to add some absolute value signs to our answer. And now it's correct. So make sure you adjust number 13. Number 14, we run into the same situation. We've got the trifecta. We've got the even index, even power, odd result. This one's going to need absolute value. So the final answer is the absolute value of n. In 15, highlight this one as well. We have another similar situation. Not with both of them though, just with one of them. With the a, we had an even index, an even power inside the index, but it ended as an odd. The n squared was fine, but the a needed absolute value. So you only want to put the absolute value around the one that needs it. So it's the absolute value of a times n squared. That should be our final answer to number 15. Now number 16 was an odd index, so we don't even need to worry about this absolute value at all, so our answer was correct as is. Now 17, you might think, oh, well, it says it wants the negative. Right, but only the negative. So if I have my negative in front, then everything that comes after it better be positive. Because if I do, because this is getting multiplied by 11, it's getting multiplied by a to the third, it's getting multiplied by b. If a to the third or b are negative, then that's going to cancel with this negative, making it positive. But I only want the negative. So I noticed that actually both of them need absolute value because they both started off as even powers, right? They were under the even index, and they both ended as odd powers. So because they both need it, you can just put it around both of them. So our final answer would be negative 11 times the absolute value of a cubed times b, which would ensure that my answer stays negative, since that's all I wanted in this case. In 18, I don't have to worry about it because my index was odd, so my answer was fine as is. And in number 19, let's highlight that one. I did have an even index there. So I had even index, and they both actually had even powers. Only the x ends with an odd though, so only the x cubed would need the absolute value. So final answer on that one should be the absolute value of x to the third times y squared. Okay, so when you're doing your classwork, you need to know both the mechanics, how you simplify the radicals, but also when you do and when you don't need to use the absolute value. So it's important to remember even, odd, the trifecta. This is the situation when you would need to use it, and then in every other situation you don't. So this requires a lot of practice. I'm sure you probably will have lots of questions. So I can't wait to see you and help you in class. Bye.